దీని వాట్సాప్ ప్లేలిస్ట్ నెంబర్ కదా మనకి చూడు ఆడిన మెయిల్ వచ్చింది చూడండి మెయిల్ వచ్చిందా ఇప్పుడు ఏం చేయలేదు సార్
అది చార్జర్ లేదా చెప్పి ఉండవు రూమ్లో ఫైనల్ వచ్చారు కదా ఫుల్ కరెక్ట్ డిలే లేకుండా
ఒకసారి బయటకు వెళ్ళి విను మాట్లాడుతుందా ఎలా వస్తుంది ఇక్కడ కరెక్ట్ వస్తుంది కరెక్ట్ వస్తుంది ఇది ఇట్లా లైవ్ కాదు మీరు యూట్యూబ్ civil engineering, organization, student Ratnama, GIS, geoinformatics, and its career. Outstanding scientific September 28th.
అది అంటే ఒక ఎక్సైజ్ కాకుండా అయిపోయిన తర్వాత స్టార్టింగ్ టెస్టింగ్ చేసిన తర్వాత నెక్స్ట్ మీరేమో కన్ఫర్మేషన్ ఇప్పుడు టెస్టింగ్ కూడా పంపిస్తున్నాం ఇలా కాకుండా నెక్స్ట్ మరి కొంచెం పంపిస్తే ఫేస్ వాల్యూస్ అవే చేయండి చాలా టెస్టింగ్ పేషెంట్ దానికోసం వెయిటింగ్ వస్తే నేను మాట్లాడుతున్నాను కదా మనకు వస్తుంది ఓకే ఇప్పుడు అది ప్రెజెంటేషన్ వస్తుంది టెస్ట్ కాకుండా వస్తుంది కదా
ఏం ప్రాబ్లం
చందు మేడం ఒకసారి సార్ మెయిల్ ఐడి పెడతారా
మీరు లైవ్ అది పెట్టారు కదా నేను కామెంట్ మీరు ఒకసారి కామెంట్ పెట్టండి
కామెంట్ ఒకసారి యూట్యూబ్లో కామెంట్ ఆప్షనా ఉందా యూట్యూబ్లో కామెంట్
వాట్సాప్ లో పంపిద్దాం థ్యాంక్స్ సార్
వాట్సాప్ పంపించడానికైనా
కాదా
అవుతుంది. మీకు లింక్ పంపించాను కదా ఇందాక మీకు మెయిల్ వచ్చింది కదా లింక్, ఆ మెయిల్ పంపించాను వాట్సాప్ కూర్చోండి సార్. సో అదే కొంచెం సార్ ఇక్కడ ఇది మ్యూట్ పెట్టుకోవాలి కదా, ఇది మ్యూట్ పెట్టుకోవాలి కదా మనం కదా. అంటే సిస్టమ్ సైలెంట్ పెట్టుకుంటే
లేకపోతే ఎక్కువ వస్తుంది.
ఫస్ట్ లో పెట్టుకున్న టీకో బాగా వచ్చింది, బట్ ఈ రెండు పెట్టిన
అంటే స్క్రీన్ కటింగ్ పెట్టారు కానీ
ఓన్లీ ఒకటి ఏంటి ఇందులో కంట్రోల్స్ ఉన్నాయి అని చెప్పేసి
ఏమంటే ఫోన్ దగ్గర పెట్టుకుంటే
అదే పక్కన అంటే మీరు సిస్టమ్ మ్యూట్ పెట్టారు, సిస్టమ్ మైక్రోఫోన్ ఆఫ్ లో పెట్టారు, కంప్లీట్ మైక్రోఫోన్ ఆఫ్ లో.
కానీ ఇక్కడ పెట్టుకుంటే రెండో వదిలి ఉండకూడదు.
ఏం ప్రాబ్లం,
ఆ బెండ్ సిస్టమ్
ఏం ప్రాబ్లం, ఏం పక్కన పక్కనే కాదు
మొత్తం ఇది రెండు
ఏం చేస్తారు.
అవునా, మరి ఇది గాడ్స్ లాగా
మీరు స్క్రీన్ రికార్డింగ్ ఏదైతే పెడుతున్నారో దాన్ని ఆఫ్ లో పెట్టాలి.
ఇప్పుడు స్క్రీన్ రికార్డ్ పెడుతుంది అనుకుంటున్నాను.
మీరు మామూలుగా సిస్టమ్ మీరు మాట్లాడుకోండి ప్రాబ్లం. అండ్
GRT@NICW.AC.in. ఓకే సరే సార్, ఇప్పుడు ట్రయల్ లింక్ పంపించాను సార్, ఒకసారి చూడండి.
సార్ ప్రెజెంటేషన్
ఓకే సార్, ఓకే కింద ప్రింటర్ పనిచేస్తుందా? ప్రింటర్
బాధపడిపోయే ఏమనుకున్నాను ఇంగ్లీష్ కూడా చేసుకోవచ్చు. అదే తీసుకున్నాయి
రికార్డ్ సిస్టంలోనూ
అది ఎప్పుడైనా చేసుకోవచ్చు. రికార్డ్ సిస్టమ్ అవసరం లేదు, దీన్ని డిస్టర్బ్ చేయదండి. ఒకవేళ స్క్రీన్ రికార్డ్ ఇది పెట్టంటే దీన్ని ఇది ఓపెన్ చేయకూడదు. ఏదైనా మూడు సిస్టమ్ ఇష్టం లేదు.
యాక్చువల్గా మ్యూటేషన్ ఎగ్జాక్ట్ టైం పెట్టమని
ఇప్పుడు పెట్టారా లైవ్ పెట్టేస్తారా?
లైవ్ అంటే కాకపోతే రికార్డింగ్ అవ్వట్లేదు.
చూపిస్తుందా?
సార్ మీకు లైవ్ లింక్ వచ్చింది. నిన్న 6 సెకండ్స్ కూడా కాదు, ఒక 1 or 2 minutes కూడా వస్తుంది. మొబైల్ నెట్ ఈ వారి నెట్వర్క్ వస్తుంది. లేదు, పాస్వర్డ్ ఏముంది అయితే లేదు.
వైఫై లేదు, ఓన్లీ ల్యాన్. ల్యాన్ ఒకటే ఉంది.
మీరు అందరూ లాగిన్ అవ్వడానికి
హలో సార్, ఇక్కడ మాట్లాడుతున్నాను. హలో హలో సార్, ఐ వాచ్ వెరీ క్లియర్ రైట్. అది యూట్యూబ్ లో బాగుంది ఈ లింక్. యాక్చువల్గా ఇదే మనది బాగుంది ఇక్కడ రైట్. సో ఇప్పుడు స్పీకర్ మనకి ఏమైనా గెస్ట్ ఇచ్చినప్పుడు ఎలా ఉందో చూసుకుని మనకు సరిపోతుంది కదా. అవసరం ఇది సరిపోతుంది, అక్కడే కూర్చుంటారు మేడం. ఇప్పుడు సార్ అయ్యారా, అదే పెట్టారు అందరూ అలాగే కూర్చో, అక్కడ కూర్చోండి అసలు వరుసగానా. మేడం ఏముంది,
మీరు అటు వెళ్ళండి, అది పక్కన పెట్టి ఇది
మేడం చైర్ తీసి రౌండ్ చేసుకొని కూర్చుంది మేడం.
ఎందుకు లేదు సార్, ఆయన అదే పనిగా చెప్పాడు. నేను
ఆడ కార్నర్ లో వచ్చాను.
ఆ చైర్ అయితే
Hello.
Good morning, sir.
Morning. Now, actually, I want to check about the sharing of the screen. See, present now. Is
Yes,
it right?
sir. Please click on present now, sir.
Yeah, present lo mood వచ్చి your entire screen window a Chrome tab అని వచ్చింది.
Entire screen select చేయండి, sir. You can select entire screen.
Okay. ఎంటైర్ షేర్ యువర్ ఎంటైర్ స్క్రీన్ వచ్చింది. ఇప్పుడు చిన్న స్క్రీన్ కనపడుతుంది. ఇక్కడ షేర్ కొట్టమంటారా?
Select the screen and click on OK. Allow.
Okay, share.
Then automatically your entire screen will be shared, sir. Now.
Okay, 1 minute. You are presenting to everyone అని వచ్చింది.
Yes, sir.
ఏం రాలేదు ఇక్కడ.
Sir, you can minimize it and you can continue the presentation.
Oh, okay. 1 minute.
Yes, now we are able to see your screen.
Okay. Mhm.
Yes, you are entering into some folders and you are trying to open your.
Yeah. Okay. You are able to see now?
Yes, sir. Sir, make it maximize.
Yeah, I 1 minute. Again, I'll open it. Yeah, correct. You're able to see? You're able to see?
Yes, sir, we are able to see your screen now.
Okay, so I'm stop sharing. I'm putting now. Okay.
Sir, please avoid your mobile, sir. It is being okay, sir. Not you, sir.
We'll make it.
So ఇంకంతా ఓకే కదా?
Sanjay madam, please keep it in mute.
Yes, sir, please continue, sir.
Okay, now I can join it. Now still there is time now.
Yes, sir.
So I join it in another 10 minutes. Is it okay?
Sir, we will send another link.
Sir, actually, we will send you one more link for the main event.
Okay.
So please, the same procedure. Please follow the same procedure, sir.
Okay. Right. Bye.
Okay, thank you, sir. Thank you very much, sir.
మైకా
Hello. Hello. Good morning, everyone. Is it audible?
Good morning, everyone. Thank you for joining in this 3 days webinar session. So we would like to start the session in 5 minutes. Please stay in online. Thank you. Thank you very much to everyone.
ఇది అవసరం లేదు. ఇది అవసరం లేదు.
కవచాలను పరిరక్షిద్దాం, కరోనా వైరస్ నుంచి దేశాన్ని గెలిపిద్దాం. మరింత సమాచారం కోసం రాష్ట్ర హెల్ప్ లైన్ నంబర్ 104 లేదా కేంద్ర హెల్ప్ లైన్ నంబర్ 107 సంప్రదించండి. భారత ప్రభుత్వం ద్వారా జనహితార్థం జారీ. నమస్కారం. కోవిడ్-19 అన్లాక్ ప్రక్రియ ఇప్పుడు దేశమంతా మొదలైపోయింది. అటువంటప్పుడు కేవలం
ఒక్క క్షణం. హలో హలో,
Sir, audible.
are you able to listen to me?
Yes, sir. We are able to hear you.
Okay, right.
A very good morning to one and all present here. Myself, Dr. J. Deepthi, working as a mentor in mathematics. On behalf of Department of Mathematics, Rajiv Gandhi University of Knowledge Technologies, RK Valley, welcomes you for all the 3 days national level webinar from 5th to 7th November. With the encouragement of our management, the Department of Mathematics RKV campus organizing this webinar on current trends in mathematical applications in engineering. We are very happy for the tremendous response and participants in this program. Now I would like to extend my warm welcome to our Honorable Director, Sir, Professor B. Sudhir Prem Kumar Garu. Good morning, sir. Now I request Director, Sir, to address the participants.
Yeah, good morning, madam. Thank you very much for inviting me for this webinar of a 3-day webinar on current trends in mathematics, mathematical applications in engineering. Am I audible, madam? Am I audible?
Yes, sir.
Yeah. So once again, I want to thank the organizers for inviting me as a chief guest for this 3-day webinar organized by the Department of Mathematics, which will be on current trends in mathematical applications in engineering. I hope, all of you are aware of RGKT, which has been initiated or started by the then Chief Minister of Andhra Pradesh, Dr. Y.S. Rajshekar Reddy Garu, for uplifting the poor of or intelligent poor of the rural Andhra Pradesh. And for this, with the noble task, this institute has been inaugurated or installed, and we got very talented people who are working in the different departments of RGKT, RK Valley. So once again, I want to invite all the eminent speakers who are going to talk or taking the invited lectures, like Professor Radha Krishnamacharya from NIT Warangal, and Dr. B.V. Haragopal of BITS Pilani, Hyderabad, and Dr. Y.N. Reddy, Mathematics of Department of NIT Warangal. And also, I want to thank the organizing committee, or I want to maybe congratulate the organizing committee also by name A. Sudhir Kumar of Department of Mathematics, Dr. J. Deepthi of Mathematics Department Mentor, and Head of the Department, Dr. M. Muniratnam. So I'm sure nowadays almost all engineering applications are basically interrelated with mathematical equations. Hope all of you are aware of that. Without mathematics, no engineering branch will sustain. If you want to take even the computer science department, or mechanical engineering department, or civil engineering department, for that matter, ECE and EEE, all are closely or maybe thickly related or maybe bounded, have the relation with the mathematics department. All mathematical equations, fundamental equations are totally coupled with the mathematical department. So it is indeed a great pleasure for me to invite all the participants who are taking part in this 3-day national webinar, which will be of high value addition program. That too, the people from NIT and BITS Pilani are going to take the classes, and I am sure you will enjoy the cream and the knowledge that is being proposed or maybe supplemented by the invited speakers. And first of all, I want to thank the organizers for giving me this opportunity.
BSc Mathematics, which we called in AP. We are organizing, coming to the webinar, we are organizing 3-day webinar, and which we divide into 3 parts. So on first day, we are dividing as applications in applied mathematics. So that given by the talk by Professor G. Radhakrishnamacharya Garu, retired professor, NIT Warangal. And second day, we divide into statistical methods, that given by Professor V.B. Aragopal Garu, retired professor, NIT Warangal. BITS Pilani, Hyderabad. And third day, we are concentrating on real pure mathematics. Third day, we are given on pure mathematics, that given by Professor Y.N. Reddy Garu, NIT Warangal. So this is about introduction about the webinar. So I hope all you are enjoying and helpful this webinar by participating. So all the participants will enjoy this webinar. Thank you all. Thank you for organizing this opportunity. Thank you all.
Thank you, sir. Thank you for giving nice introduction about the department. I know that every participant is eagerly and enthusiastically waiting for the energetic talk. Now it's time to introduce today's speaker and chief guest of today's webinar. It gives me immense pleasure to introduce today's speaker, Professor G. Radhakrishnamacharya Sir. He has a vast experience of 40 years, of which he has 34 years teaching experience at NIT Warangal, 2 years at IIT Kanpur, and 2 years at NIT Tadepalli. And presently he is working as a professor of mathematics at Indian Institute of Information Technology, Design and Manufacturing. He also has international experience of working at University of Kolkata, Nigeria. He has guided 11 PhD scholars and has published 80 research articles in various international and national journals. He also guided 52 students in various DSc projects. He served as a registrar of NIT Warangal during 2004 to 2005 and acted as a co-convener of LSET and ESET exams of both Telangana and United States. He also worked in various administrative positions such as staff advisor, member of UC and PG Admission Committee at REC Warangal, hostel warden, heavy job, member, board of studies of various universities. There are much more interesting facts about Professor, but due to time constraints, we will start the session. Now, I hand over the session to Professor G. Radhakrishnamacharya Sir. Sir. Thank you,
Yes.
Sir, please unmute your mic, sir.
Hello.
Yes,
Hello?
sir. You are audible now.
Actually, earlier, when Deepthi spoke, the voice was not at all clear. Is it clear now? The voice, is it clear?
Sir, now it's very clear, sir.
Okay. Now, do I start with the technical talk or is it still inaugural function?
Please give some brief introduction and then we'll continue talk.
No. Do I talk in general, later the technical talk follows, or do I start?
Yes,
Do I straight away start the technical talk?
then sir, please start, give some general, sir, then later we'll follow technical, sir.
Okay. Yeah, very good morning to all of you. I hope all of you are able to hear me. Honorable Director, Honorable Head of the Department, Dr. Deepti, other faculty members of the Department of IIIT, Pulivendula, Idupulapaya, and other participants to the webinar. A very good morning to all of you. At the outset, I would like to thank the organizers of this program, in particular, the director of the institute, the Department of Mathematics, and Dr. Deepti, for giving me an opportunity to be with you this morning, interact with all of you, and share some of my views with all of you. As you all know, the whole world is passing through a very critical phase today. The entire mankind is at war, nothing short of a third world war, but against an invisible enemy. We are not able to see the enemy, and the whole of mankind is struggling. But when you are at war, you cannot keep worrying. You have to think ways to get over the difficulty and win the war. So we cannot bow down in this situation. We cannot crumble. We should not crumble in this situation. In fact, every crisis gives rise to an opportunity. An optimist sees an opportunity in a crisis. So we see today the trends, the whole of the lifestyles of mankind has changed today. We see the change in the mindset of the entire world today. Online teaching has become order of the day today. It may be, whether we like it or not, it has been indispensable today. The crisis has given rise to many new inventions. Many people have invented new devices, appliances, and so on. So, every crisis, you see, during Second World War, the subject of operations research was born. During Second World War, when there was shortage of men, shortage of arms, and so on, the administrators called all the scientists and said, we have this problem, please try to resolve this issue. They all joined together and formulated some solution, which ultimately turned out to be the so-called operations research, because it was born during military operations. It is called operations research. And today, you see, operations research or optimization technique has permeated all disciplines of engineering, all branches of science, all walks of life. And so also, this particular crisis created by COVID-19, coronavirus, we should take it an opportunity. We should think of ways to get over the difficulty. We should adapt to the new situation and find ways to start our regular life. If we keep worrying, there is nothing we are going to achieve. So let us take it as a challenge. Let us take it as an opportunity and get along with our work. In this context, the webinars have become an order of the day. In fact, last few months, I myself have given about 20 to 25 webinars. So I congratulate the Department of Mathematics of IIIT Idupulapaya for taking this initiative and organizing this webinar, because otherwise, when you keep away from the routine work, we tend to become complacent. We tend to forget our subject, fundamentals and so on. And coming to mathematics, actually, as we all know, mathematics is the basis for everything. And I am told that the audience consists of students as well as faculty also. I do not know exactly what is the composition. So if the audience, the heterogeneous audience, sometimes it is difficult to address them. If it is a student community, there is one way of addressing them. If it is faculty, there is another way of addressing them. When it is a mixture of both students and faculty, it becomes slightly difficult, because students, we have to talk in a particular wavelength. If it is faculty, you have to talk in another wavelength. Anyway, if it is a mixture of both, I'll have to balance between the two. And second thing is, as I told, last 3-4 months, I have given several webinars, maybe 25 to 30 webinars I would have given. So some of you would have already attended. Possibly some of the topics which I'm going to talk today, they could be repetitions of the earlier contents of my earlier talks. So if it is repetition, kindly excuse me. I cannot speak new in every webinar. I'll have to repeat the same topic, same content many of the times. There could be a lot of commonality. So that is another possibly constraint or limitations which I should tell you honestly. Now, coming to this particular webinar, as I told, it is the applications of mathematics in engineering. In fact, the students tend to think, most of the students, either at school level or intermediate level or degree level, they tend to think that mathematics is only one subject like any other subject. Like in school, they study languages, they study social science, they study natural science, they study history, sociology, economics, mathematics, and so on. So they think mathematics is like any other subject. So they need mathematics to get good marks, get a good seat in +2, then get good percentage in +2 through mathematics, and get a good seat through either MSET or IIT mains, JEE mains, whatever the case may be. Get a seat in a good reputed institute. And first year, possibly you study mathematics. Maybe second year, after that you don't need mathematics at all. So they think the role of mathematics ends at that point of time. That is a totally false notion. Mathematics is indispensable to every branch of science, every discipline of engineering. So the teachers, it is the responsibility of all the teachers to make the students realize that mathematics is not merely a branch, a subject which you study like many other subjects. It is much more than that. As I told, mathematics is not merely a subject. It is not merely a branch of science. Mathematics is a way of thinking. To be mathematical means to be logical. To be mathematical means to be rational. To be mathematical means to be precise. So you see, in many of these exams, aptitude test exams, banking, railway recruitment, and so on, CAT exams, you will find many questions from mathematics only. The reason being, if you are good at mathematics, you will be good at any other subject. So mathematics, for example, in mathematics, we believe in precision. When we say A by B, we say B not equal to 0. When we say dy by dx, provided the limit exists. When we say integral so and so, provided the integral exists. Because we know that in some of these cases, the integral, the limit, they may not exist. For example, we take an infinite series, provided the series is convergent. Series may not be convergent. We know the limitations of these particular concepts and techniques. And mathematics is a philosophy. Mathematics is an universal language. mathematics is the language of nature. This is not my, word. It is the famous words of Galileo. Galileo, famous scientist, said, if you want to understand nature, you need a language. The language you need to understand nature is the language of mathematics. And this subject, in this language, the alphabets are triangles, circles, ellipses, parabolas, straight lines, quadrilaterals, and so on. Without the use of these symbols, without the use of mathematical concepts, you will not be able to understand nature at all, and you will be wandering in darkness. That is what Galileo told about the mathematics being the language to understand nature. In fact, there are many examples. I will not go into the details of them. You take pi, for example. You take Fibonacci sequence. You take golden ratio. You take logarithmic spiral. Logarithmic spiral, we study a curve called logarithmic spiral in mathematics. You take, you look at the sky during night. You find constellation of stars. You cut a cabbage, you will find some sort of curves. They are all mathematical curves. If a drop of water is a sphere, you find so many situations where you will find these mathematical figures. And you see, in nature, you have periodicity. In mathematics, we have periodicity. In nature, you have patterns. In mathematics, we have patterns. In nature, you have regularity. You have continuity. You have irregularity. You have discontinuity. In mathematics, we have regularities, irregularities, continuities, discontinuities. Every situation you find in mathematics, we have a concept in mathematics. For example, you find lightning. Suddenly something comes with a very high, potential or very high magnitude and disappears. We have some function, impulse function we call in mathematics. For every situation you find in nature, we have a concept in mathematics. We have a function, an entity in mathematics. That is the beauty of mathematics. It is the language of science and technology. It is the heart and soul of science and technology. But for the abstract and consistent findings of mathematics, many important discoveries would have eluded humanity. You name any important discovery in any branch of science, in any discipline of engineering, invariably mathematics would have been the basis for all such discoveries, for all such inventions. Mathematics permeates all branches of science, all disciplines of engineering, all walks of life, and all spheres of activity. In mathematics, another beauty is there is no redundancy in mathematics. Every concept we study, it finds applications somewhere or other. I may not know the application. The mankind may not know the applications today, but invariably a well-formulated, well-conceptualized topic in mathematics finds applications somewhere or other. Every theorem in mathematics has a history. Every result has a story. Every equation has a beauty. Every concept has an application. You see, for example, Srinivasa Ramanujan, he died in 1918, more than 100 years ago. He gave thousands of theorems. Whether he knew about the applications of those concepts, we do not know. But today we realize that most of the results given by Srinivasa Ramanujan, they find applications in diverse areas like acoustics, holography, communication theory, signal processing, and also latest subject like string theory. And another thing is black holes. I think you know the story of Srinivasa Ramanujan. When I will not go into the details, he was a mathematical prodigy. In fact, Srinivasa Ramanujan, actually, he was a sort of a mystery, an enigma, a Swayambhu. Swayambhu means self-made personality. Nobody taught him anything, but he acquired them on his own. How, of course, we don't know. Let us not go into the details. In fact, I will not go into the details of all those things. But you see, it is said that the contributions made by Srinivasa Ramanujan during, he died at the age of 32. Forget about first initial years, about 7-8 years. Maybe say around 20-25 years. You forget about another 5 years. In 10-15 years, the contributions made by Srinivasa Ramanujan, in fact, one European mathematician commented, the contributions of Srinivasa Ramanujan are much more than the contributions of all the European mathematicians put together during the last 50 years. That speaks volumes about the contributions of Srinivasa Ramanujan. And why I'm talking that is, most of the concepts he gave, they find applications today. Subjects which we think are normally pure, which you do not find applications, today they are applicable somewhere or other. In fact, I'll tell you one interesting instance. In 1976, one American professor accidentally visited a library in London. He asked the librarian, please give me some latest book in mathematics. The librarian said, I don't know anything about that, but there is one box lying in the corner. Nobody has touched it for a long time. You can go and see. So that professor went and opened that box, and he found sheets, handwritten sheets around 120, 130, written in black ink. Then he took them out. He had a look at them, and he was amazed at the complexity of mathematics, at the elegance of mathematical equations given. They are known as, today we call them Mach theta functions. And today people realize that Mach theta functions are needed to comprehend the incomprehensible black holes. Black holes, as we all know, is a very, very tough subject. To understand that, the concept of Mach theta functions are used. And also today the whole world depends upon computer. And in computer, we need security. If there is no security, there is a lot of risk, because all our transactions take place through computer, our banking transactions, defense transactions. We correspond with people through net. If there is no security, there is a lot of risk. So in providing security, all these things, the concept of Mach theta functions, they prove to be very useful. So these examples show that every concept in mathematics has an application. That is the beauty of mathematics. That is the fascination. In fact, we all know mathematics is called the queen of sciences. Why it is called queen? We all know the British queen is supposed to be a beautiful woman. And so is the case with mathematics. Mathematics has got intellectual beauty. Mathematics has got aesthetic beauty. Many of the concepts, for example, whole of electromagnetic theory, when you translate into the mathematical domain, they result in what we call Maxwell's equations. So you see Faraday's law, Coulomb's law, Ampere's law, Ohm's law, so on, so on, so on. You represent them in terms of gradient, divergence, curl. You follow? In fact, there is a very interesting anecdote involving Albert Einstein. Albert Einstein, it seems, he was obsessed with physics during his college days. And in the process, he used to skip other classes, class of other subjects. He would ask one of his friend, please write the notes for me. I will copy it from you later. So his friend used to write the notes, and Einstein, because he was a genius, used to study later, and he passed with the flying colors. Later, he went on to become an eminent scientist, and he started working on a problem. And his intuition told him he's working on a path-breaking topic. But the mathematics turned out to be very, very haphazard and clumsy. He did not know what to do. Something is wrong. I need to use something else, some other concepts, some other equation, some other notion. He did not know. He asked many people. They could not help him. He went back to his college friend who used to write the notes for him. My dear friend, I am working on a problem. My intuition tells me it is going to be a path-breaking result. But I think I need to use some other mathematical concept. I don't know what is that. Then his friend looked at the notes and said, you fellow Einstein, you missed many class of mathematics. In mathematics, we study what is called a tensor. And the tensor we represent using a matrix. I think if you do that, your problem will be solved. Einstein, he was a genius. So he studied tensors and used them. And the whole of the clumsy and awkward looking, haphazard looking mathematics got reduced to a beautiful looking, elegant looking equation that turned out to be theory of relativity. Then Einstein tapped his head and said, unnecessarily, I missed the class of mathematics. Had I attended those classes of mathematics, I would have given this theory of relativity 3 years earlier. The moral of the story is, students should not miss any class of mathematics. The point here is that every concept we study will have applications somewhere or other. I may not need those applications. I may not need it now. I may need it else some other time. So if you know those concepts, they would remain in your subconscious mind. And when you need something, your mind tells you, I think you have studied something which is needed for the situation. You're able to recall. So that shows that the indispensability, applicability of every concept we study in mathematics. In fact, as I told you, many examples can be given. I don't know what is the time now. It is already 10:55. So I'll quickly run through some, applications of concepts of mathematics. Simple concept is, for example, we all go by a car, motor vehicle, right? And motor vehicle, there is what is a headlight. The headlight is the application of the mathematical concept of parabola. We know parabola is, we all study at +2 level, conic sections. The concept of conic sections were given 2000 years ago by Grecian mathematicians. They were very fond of geometry. Whether they knew about the applications, we don't know. And later, 16 centuries later, German astronomer Kepler, after painstaking study of the sky, gave 3 laws of planetary motion. One law says every planet traverses an elliptic orbit. So in this situation, so when he was trying to study the motion of a particle, so suppose a particle starts at a point at a particular time with an initial velocity, where it would be after some time and so on. We all study in the high school level. When he finished it, he realized not only he could describe the motion of a particle, we have given so many formulas, S is equal to ut plus half at square and so on and so on. So he understood not only he has described the motion of a particle, but he came up with what is called calculus. Calculus, limit. The concept of limit is considered as the greatest creation of human mind, because without limit there is no continuity. Without limit there is no differentiability. Without limit there is no integrability. Without limit there is no convergence. Without limit there is no differential equation. Without differential equation there is nothing. Everywhere, every branch of science, every practical situation, we are concerned with rate of change of linear momentum, rate of change of angular momentum, rate of change of population, rate of change of profit, rate of change of entropy, rate of change of electrical energy, and so on. The moment you say rate of change, derivative comes into picture and differential equation is formed. So that is why limit is considered as the greatest creation of human mind. You take Albert Einstein. He was trying to explain the inconsistencies in the Michelson-Morley experiment, and he came up with theory of relativity. As a corollary, he got the equation E is equal to mc square, which gave birth to atomic theory. So you see how the mathematical concepts formulated, they give rise to birth of subjects, birth of new theories. Today we study, for example, I don't know how many of you must be knowing the so-called 4-color problem and the 7 bridges problem, right? These problems gave rise to the so-called subject of graph theory. And today you see graph theory, it has got so many applications in computer science, networking, in behavioral science, psychology, and so on. And these are all because of the concepts given by mathematicians. Why you take, for example, many times the concepts are proposed by eminent people, they look like simple puzzles. Why Fibonacci? Fibonacci proposed a simple problem. Fibonacci, I will not go into the details of that. He proposed a simple problem and it looked like a small puzzle which we all play at school level. Suppose there is a pair of rabbits, one male and one female, right? A pair which is older than a month produces another pair. At this rate, how many pairs would be there after 12 months? How many pairs would be there after n months and so on? This looked like a very simple problem. But we all know it gave rise to the sequence of Fibonacci 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, and so on, so on, so on. Today we find it has got so many applications. The golden ratio, the divine number, 1.61. The relation between divine number and the golden ratio. We follow? So their relevance in nature, if you look at them, we understand why Galileo said mathematics is the language of nature. Pi, for example. So these things show the beauty and fascinating of mathematics. You take, for example, a simple graph theory. We all play chess, Of course, I don't play, but I know about chess. You take a chess, a 8 by 8 chess board. For example, you say, suppose somebody asks a simple question: how many queens are needed so that they cover all the squares? How many squares are there? 8 by 8, 64 squares are there. How many queens are? What is the minimum number of queens needed to cover all the squares or to attack all the squares? For example, whatever you may say, for example. Of course, one simple answer is, you simply say you need 8 queens. You put 8 queens straight, it covers everything. That is not a very difficult thing. What is the minimum number? You follow? The minimum number is, that is what we call, domination theory, domination numbers. You follow, for example, somebody can note down and check. You put 1 queen in the 1, 1 square, 1, 1. Another in 2, 3. Another in 3, 5. Another in 4, 2. Another in 5, 4. You can check later. 5 queens, they cover all the 64 squares. I repeat, ask what is the importance of this? It's just a game. That is true, it is a game. But you see, many times, for example, in reality, you want to put for example, say some internet, you are working on that. How many nodal points, how many routers should be put? Say surveillance stations, defense establishments, some particular this thing, I want to cover this entire area. How many stations, how many kiosks I should have? In order to do these things, this particular theory, dominating number, domination theory, which we study in graph theory, it is being used. You see, many times, great people, when they propose, they look like simple puzzles. They look like child's problems, but they give rise to birth of many subjects, which will have a tremendous effect in many disciplines, in many physical situations. Today, man has advanced so much. As we know, necessity is the mother of invention. When there is a problem, as I told earlier, operator was born during Second World War. Why? It is out of sheer necessity. And today, you see so many appliances, For example, you don't want to touch anything. So people have got appliances, without touching that. For example, lift we go. We touch the lift, they gave birth to several subjects. For example, Srinivasa Ramanujan, once he was, when he was in England, there is a famous statistician, Mahalanobis. He posed him a simple problem. He thought it is a simple problem. But the way Ramanujan replied immediately, continued fractions, it was something amazing. Similarly, we all know that when Ramanujan was in the hospital on the sick bed, Hardy went to see him. He did not know how to start the conversation. He simply told him, Ramanujan, I traveled by a cab. I'm sure all of you must be knowing this. I traveled by a cab. The number of the cab seems to be a dull number. He said 1729. Immediately Ramanand shot back. No, Professor Hardy, it is not a dull number. It is a very interesting number. Hardy was surprised. What is so interesting about that? He said it is the smallest number which can be expressed sum of two different cubes, 10 cubed plus 9 cubed, 12 cubed plus 1 cubed. And today we find it has got so many properties. It is called Ramanujan number. It is called taxi cab number and so on. You see 1 plus 7, 8, 8 plus 2, 9, 9 plus 1 plus 7, 17, 1 plus 7, 8, 8 plus 2, 10, 10 plus 9, 19. You reverse it, 91. 19 into 91, again you get 1729. So you take so many properties, that is the greatness of these genius people. That's why we said Ramanujan was a prodigy, a mystery, an enigma, a swayambhu. Those people, whatever they speak, they give rise to new subjects. And today we realize all those concepts find lots of applications. So I told about these things. And you see today, when we go to a doctor, the first thing doctor sees is pulse. First thing doctor normally, of course, today because of corona, people may not touch. But normally when you go to a doctor, the first thing doctor sees is pulse. It tries to feel the pulse and tries to understand the working of the heart. When I go to my technical talk, maybe I will explain about it. So this pulse depends upon the mathematical concept of simple harmonic motion. And, the pulse, olden days, there were no thermometers, there were no x-rays, there were no scans, no blood tests, nothing. They used to tell everything by looking at the pulse only, by feeling the pulse only. So such an important pulse depends upon the mathematical concept of simple harmonic motion. You take, for example, cricket matches. Today IPL is going on. We have test matches, we have one-day matches, we have T20. In T20 or one-day matches, when there is a rain, when the match is curtailed, how is it decided? We all know it is decided by what is known as Duckworth-Lewis formula. Who are these Duckworth and Lewis? They are two eminent mathematicians. Using the concepts of optimization techniques, they gave this Duckworth-Lewis formula. Of course, I don't say it is the best option. Earlier, something else was used. Today, they find this is the best one. People are still working on it to improve it. That is a different story. But today, the system being used, the concept being used to decide the result in a rain curtailed match is Duckworth-Lewis formula given by mathematicians. We all use mobiles. In mobile, there is nobody who doesn't use a mobile today. We are able to talk to somebody who is in America. We are able to see the images. How? It is because there is a antenna. The antenna is based on a mathematical concept called fractal, F-R-A-C-T-A-L, fractal. The concept of fractal was given by Mandelbrot in the year 1982. Fractal geometry is a generalization of what we call classical two-dimensional geometry, Cartesian geometry, classical geometry. And what is fractal actually? Very roughly speaking, it is a fractional dimensional entity or an infinitely divisible or self-similar entity. You follow? In mathematics, the real analysis, we study what is called a Cantor set, a 0-1 closed interval. What is that we do? We divide it into three parts. 0, 1 by 3, 1 by 3, 2 by 3, 2 by 3, 1. Remove the middle third. You are left with 2. 0, 1 by 3, 2 by 3, 1. Then again, each one divided into three parts. Remove the middle one. Ultimately, you get what is called a Cantor dust or Cantor sequence. It is based on this concept of Cantor set. Today, the fractal geometry. And today, fractals find so many applications in geophysics, because in nature, many things are not of regular shape. You take the anecdote, very small anecdote, very funny anecdote. Somebody was going in a balloon, a small balloon, parachute type, Then it developed some technical problem. It simply landed somewhere. Since it landed somewhere, he did not know where he was. He looked around. He did not know where he was. Somebody was walking. He said, "Sir, can you please tell me where I am?" That man said, "You are in a cornfield. You are in a parachute and your parachute is in a cornfield. This man asked him, sir, are you a statistician? He said, yes. How do you know? Then he said, the information given by you is precise, correct, but absolutely useless. So people used to think statistics is a useless subject. But today we realize statistics is indispensable everywhere. Today we talk of artificial intelligence, we have BTech artificial intelligence, right? Data analytics, big data, data science, everywhere you need statistics. In fact, statistics, linear algebra, little bit of computer programming, these are things you need to initially understand artificial intelligence. In fact, I taught for 35 years at NIT Warangal, small correction. I taught for 35 years at NIT Warangal. I retired from Warangal in 2018. For 2 years, I was at NIT Tadepalligudem, and here I joined IIIT DM Kurnool. It is also a institute of national importance under Government of India. So Warangal, the BTech students, after 25 years, they have what is called a Silver Jubilee reunion. In 2016, the batch which passed out to, they came and met me after 25 years. They told me, sir, how are you? You taught us statistics. It was so interesting. They told me, sir, if you know anybody, student, who is good in statistics, who is good in the fundamentals of mathematics, please tell them to contact us, because it is we really need people who have got reasonably good knowledge in the fundamentals of mathematics and the elements of statistics. For them, sky is the opportunity for them. They have so many opportunities. And you see, artificial intelligence today, you go everywhere, we talk of artificial intelligence. You go to bank, SBI, you need only one based on artificial intelligence. Amazon, Flipkart, everybody use. For example, I go and buy something. They try to get information about me. Radhakrishna, what is he interested in? So they try to analyze, keep those products. Everywhere it is artificial intelligence. Diseases, for example, asthma, games. There is a game called Go, AlphaGo. I will not go into the details. And they have using the artificial intelligence, they could beat the #1 player in Go. That is a potentiality of the so-called artificial intelligence, for which mathematics is the basis. Similarly, we talk of fuzzy today. I think you all know fuzzy. Today, the washing machines, fans, many of the appliances, they use the concept of fuzzy. In fact, in Karnataka, there was a problem. The farmers wanted water. Government, if releases the water, there will not be sufficient water for electricity. If water is not released from the dam, the crops would wither. So they had a problem to release water or not, to release how much water should be released. Then they contacted the ISA Bangalore Civil Engineering Department. Using the concepts of fuzzy mathematics, they give the solution. All these things go to show how potential is mathematics. In fact, I always tell students, that I don't say you come to mathematics only. You study any degree. You go to engineering, you go to medical, you take economics, you take arts, whatever you want to take, you take. But try to understand the importance of mathematics in your subject. One of my colleagues at NIT Warangal, his son studied MBBS from JIPMER. After that, when he completed his MBBS, my colleague asked me, Radhakrishna, my son wants to talk to you. He came and told me, what do you want? He said, uncle, please teach me abstract algebra, modern algebra. I said, you are a student of medicine. Why do you need? No, uncle, we need them in genetic theory. So earlier people used to think natural science and physical science are too different. But today people realize that if they work together, they can make wonders. IIT, they are starting a medical programs. Today we have biotechnology, bioinformatics. In biological systems are one of the most optimal systems. Later in my talk, I will tell. And if you use the concepts of mathematics, engineering, you can do wonders. That is why now the boundaries, demarcation between these two ends, it is slowly disappearing. In fact, knowledge is only one. It is for our convenience. We made this demarcation, this compartmentalization. We should come out of that. then what we call, out of box thinking. When we do that, then only we can do what, as I told you, these fractals. Normally we say 1 dimension, 2 dimensions, 3 dimensions. Can we think of fractional dimension, 0.6 dimension, 1.2 dimension? We are not used to that. We think it is incorrect. God did not tell there is only 1 dimension, 2 dimension, 3 dimensions. So somebody thought of this fractal dimension. Fractal dimension gives you 1.2 and so on. So they could think of many, like Koch curve, Sierpinski triangle, and so on. Many they have generated using what is called IFS, iterative function system. This whole of what you call fractal geometry, it depends upon the concepts of topology, function analysis. In topology, function analysis, we study contraction mappings, we study, so many concepts. They are used in developing these fractals, which find so many engineering applications today, right? So I think I will take, as I told you, engineering students, for example, they may study 2 courses of mathematics, 3 courses of mathematics, whatever it may be. I always used to say, if you are strong in the fundamentals of mathematics, you will be able to do deeper research work when you ultimately become a scientist. In fact, realizing the importance of mathematics, NBHM, National Board for Higher Mathematics, they organize summer internship, winter internships for students of engineering. I myself recommended many students from NIT Warangal. It is a 4-week program, 6-week program. I don't know whether they are there or not today. Earlier they were there. Students who attended the program, they came back and told me, sir, today our perception is totally different. Earlier we used to think we will complete our BTech, get a good degree, go to US and make a lot of money. But today we realize the real satisfaction lies in working in our core area. And for that you need deeper knowledge of the fundamental concepts of mathematics. You see, a tree with weak roots cannot grow tall. If the roots are weak, suddenly it may grow. There it stops. If the roots are strong today, it may not grow because of some adverse conditions, but one day it will grow. Similarly, if you possess strong fundamental concepts of mathematics, even if you don't get a good admission in a good branch, good institute, but your knowledge will definitely reward you. Hello? 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 Hello?
Hello,
Are you
sir.
able to hear me?
Yes,
Are
sir.
you able to hear me? Yeah, okay.
Yes,
okay.
yes.
Yeah, in between the connection was lost for some few, I think, seconds. Okay. Now, I'll present a few cases, sir. Let me share the present now. Entire screen. Yeah. Fascinating world of mathematics and its applications of biofluid dynamics. Okay, what I will do is, what is mathematical modeling, right? This requires translation of real world problem as a real world model with a specific goal. A model retains only those features, characteristics which are relevant and significant from the point of view of goal. Then real world model is translated in the language one can conceive of. A model is said to be adequate, satisfactory if it is adequate for goals in the mind of the modeler. Step 1. Define the problem clearly and unambiguously. The problem is then transformed into a real world model with a goal of study. This may require prior knowledge about the real world associated with the problem. If the prior knowledge is not sufficient, then one has to design an experiment to obtain new additional knowledge. Step 1 leads to an initial description of the problem based on prior knowledge of its behavior. This step is a process of simplification and idealization, keeping in view the goal of the study. It leads to a real world model. It is a crucial step in model building and requires a deep understanding of the physical aspects of the system.
Sir, sorry for the interruption, sir.
The real world model is related to a mathematical formulation. It involves 2 stages: selection of a suitable mathematical formulation and then relating the variables of the formulation with the relevant features of the system. The physical features are plotted in terms of mathematical symbols to give mathematical model. Strong interaction between the physical features of the system and the abstract mathematical formulation is required. Analysis. Once a mathematical model is obtained, its relationship with the physical world are temporarily discarded and the mathematical formulation is solved, analyzed using mathematical tools. This is done purely according to the rules of mathematics. At this step, one needs to assign numerical values to various parameters of the model to obtain a model behavior. Parameter estimation using given data. Validation. In this step, the formulation is interpreted back in terms of the physical features of the problem to yield the behavior of the mathematical model. The behavior of the mathematical model is then compared with that of the given problem in terms of the data of real world to determine if the 2 steps are in reasonable agreement or not according to some predefined criteria. This is called validation. If the model passes the test of validation, it is called an adequate model and process comes to an end. Otherwise, one needs to backtrack and make changes either in the description of the system or in the mathematical formulation itself, and the process starts from there again. It is a sequential feedback procedure which requires interdisciplinary approach. How to use mathematics? You see how real world, from their idealization, approximation, you go to a real model. Abstraction, symbolic representation, you go to a mathematical model. Then mathematical theories and techniques, you apply and solve it. Then conclusions and predictions, you compare it with the real world problem. This is, in nutshell, the concept of in mathematics. What we do is, we do mathematical modeling. I think we all study in engineering, the concept of the problem of radioactive decay. Radioactive decay, you try to convert a real model, then you can transform to a mathematical model. We get a first order differential equation, then solve it, then you get the solution. From that, try to interpret in terms of the real world problem. This validation is very, very important. When you go to your doctor, for example, you give blood, say for example for corona, COVID, you give blood sample, they test the blood sample. Suppose you have very severe symptoms of corona, that the test says negative, then the doctor gets a doubt. There is something wrong with the test. Many times we see today, many times it happens. In the first time, it turns out to be negative. Then they use some other test, it becomes positive. Suppose I have given my blood. Somebody has given the blood who is corona positive. The blood samples are mixed up. I don't have corona. They say you have corona. Then they ask you, do you have any symptoms? I don't have any symptoms. They get a doubt. Again, they examine. So this is what is called validation. In mathematics also, we use validation. If something is not proper, in fact, later I'll come to that. Today, the epidemiology is playing a very important role in understanding the spread of corona, COVID-19. I'll give you a mathematical model which has become very important in the present scenario. A coupled model of fighting armies. Yeah, you see, a simple model. I've explained what is the concept of mathematical modeling. In fact, initially I explained about the philosophy of mathematics, applications of mathematics. Now I'll give some case studies. See, these are all normally which you don't study in the curriculum, but a situation, a physical situation, normally we do not think of applying mathematics to that. This is applying mathematics. In fact, there is a military strategist called Lanchester. He wanted to study the fighting of wars between two countries, two armies. So he tried to construct a model. So we'll consider a very simple model, Consider that at some time t, we have populations ft of friendly troops and et of enemy troops. Let us assume the rates of change of their respective populations are proportional to the opposing combat forces size. Ft, for example, this is friendly force, let us say Indian Army. Df by dt, the rate at which Indian Army changes, that is increases or decreases. It cannot increase, it has to only decrease. That's why I put a negative here. And it is proportional to the enemy army. Suppose you are fighting with Pakistan, you are fighting with China. Chinese army size is large, their armory is more. So the rate of our decrease is more. Therefore, it is, if you remove this one, it is proportional to enemy army size. And it decreases, so we put a negative sign. And if you remove the proportionality, we have got the constant of proportionality, lambda E et. Just like we study radioactive decay. The rate at which it decays depends upon the amount of radioactive material present. When you have 100 grams, how much decay is there? When there are 10 grams, how much decay is there? So it is simple, based on simple common sense principle. Similarly, here Ft depends upon Et and so on. Similarly, dE by dt is minus lambda f into Ft. You see, this is a very simple example, unconventional example of applying the simple concept of differential equation which we study in the first year of either BTech or degree, and to a very unknown domain, fighting of armies. Next, lambda E represents the effectiveness of the enemy and friendly forces with interesting units. Lambda E is the loss rate per unit time of friendly troops per enemy troop. You see here definition. Lambda E is the loss rate per unit time of friendly troops per unit troop. For one soldier of the enemy, how much of our friendly army is getting lost. So if lambda is larger than lambda f, enemy troops are more effective because more friendly troops are lost per unit time and per unit of enemy forces. So combining 1 and 2, so you go back, you combine 1 and 2, you get a second order differential equation. D square f by dt square equal to minus lambda E lambda f into Ft. So this is here they are first order differential equations but coupled equations. EFT and EFT are unknowns. So both the equations contain unknown, they are coupled first order differential equations. So by combining them, we got a second order uncoupled equation. It is simply Ft is the unknown here, second order linear equation. We'll show how we can obtain a lot of information without formally solving the equations. Multiplying 1 by lambda E Ft and 2 by lambda E Et, you get, and so sorry, there's a small error here, lambda F Ft. So you go back 1, you multiply lambda F Ft, lambda F Ft, and lambda E Et, so you get 4 and 5. Then since the RHS of 4 and 5 are the same, you see here lambda E, lambda F, FTET, lambda E, lambda F, FTET. Since the right hand side are same, we equate the left hand side. So you go back. Lambda F, FT, dF by dt equal to lambda ET, dE by dt. Right? This gives d by dt of lambda F, F square minus lambda E square. You can just see lambda F is a constant. So you remove that one. If you differentiate 2ft dF by dt, then minus lambda E into 2et into dE by dt. So this is same thing. So this is d by dt of lambda F, F square minus lambda E square equal to 0. D by dt of something is the first order differential equation, alternate differential equation. So this is equal to lambda F, F square minus lambda E square equal to a constant. A simple deduction, right? Now we'll see what are the initial conditions. Enemy army at time t equal 0, initial to begin with, we call it E0. Friendly army at time t equal to 0, we call it F0. Since we said, you see, go back. Sorry. Since we said this is constant, lambda F, F square minus lambda E square equal to lambda F into F0 square minus lambda E into E0 square. Or if you simplify, lambda F into F square minus F0 square equal to lambda E into E square minus E0 square. Simple equation we get. This equation is called Lanchester's square law. As I told you, Lanchester was a military strategist, an engineer. He tried to model fighting armies using the concepts of mathematics, in particular differential equations. We can use this equation to calculate the final size of winning army. The enemy force have been annihilated without solving any differential equation. Using this, actually, you don't have to solve this one, but when the enemy force have been annihilated, that means when the enemy army is defeated, then how much of the friendly army will be left? For example, how many India, let us say India, Pakistan is defeated, but still, suppose you start with 2 lakhs of soldiers. All the 2 lakhs will not be there when we win. Some forces will be lost. How much of forces do we lose? For example, you may not be, you would not possibly, you were not born 1971. India fought a war against Pakistan and liberated Bangladesh. Ultimately, it was a 14-day war. All the Bangladesh, Pakistan, East Pakistan soldiers, 90,000 soldiers, they surrendered to India. So India won the war. It was a very comprehensive victory. But still, India lost many of the soldiers. So before you go to a war, you should estimate what are the strength of the enemy and how many forces are we likely to lose. Suppose you start with 5 lakhs. What is that you are going to, suppose you say you want to occupy, they have occupied some area. You want to capture it back. And suppose going for that particular war, you are going to lose, say, lakhs of soldiers. Then you may think, is it really worth it? We are losing so many soldiers. So many planes will be lost. So many tanks will be lost. So we'll have to do lot of analysis before we embark on that particular war. So this gives you simple. Let us assume that victory is declared when all of the enemy forces are gone from the scene. In this case, E finally equal to 0. Then using 9, we get number of friendly troops remaining as. So you go back. E finally is 0. So E finally is, E finally is 0. From this, what is that you get now? F final square equal to F0 square, lambda by lambda F into E0 square. So what is the final size of the friendly army left? So this is the initial size of the army minus some factor. So this depends upon the initial size of the enemy army and these particular parameters. So even in victory, the number of surviving friendly troops is reduced by an amount proportional to the square of the initial size of the enemy force. You see, even when we win, the surviving friendly troops is reduced by an amount. So by this amount, the friendly troops is going to be reduced. Since it depends upon the square, we call it the so and so. Then dependence of the friendly and enemy forces on the respective squares have intriguing consequences. Now, we want to see two strategies. Suppose that two equally effective armies oppose each other. This means lambda E equal to lambda F, and the Lancheth's square law becomes F square minus E square equal to F naught square minus E naught square. Suppose two combat scenarios were being considered by military planners. In the first scenario, a friendly army of 50,000 soldiers faces an enemy force of 40,000 and then a second enemy force of 30,000. So it is a sequential one. You have 50,000. If enemy force, first you have 40, then you have 30. In the second scenario, the same friendly army meets an enemy force of 70. In the first case, 40 and then 30. In the second case, total 70. That means meets the same number of enemy troops assembled for a single fight. So we have to see from the strategy point of view. In the sequential scenario, the friendly army prevails in the first of its two battles with a surviving force of 30. So you see here, you apply this particular one, you apply this particular equation. 50,000 square minus first one is 40,000 square. So you are left with 30,000 square. Then 30,000 square. So you see the second sequence, second 30,000. So second 30 plus 30. It is just enough to force a draw with the enemy in second battle. Suppose the armies meet in second scenario, then you have 50,000 square minus 70,000 square, then we lose the war. So this shows the strategy important. This model has modeled the outcomes of famous battles such as Iwo Jima. Iwo Jima is the island south of Japan. Second World War, a fierce battle was fought in this island of Iwo Jima because it was very important for the both. The Allied forces wanted this one and the enemy also wanted this one. So he has modeled this one. So you see here, suppose if you want to fight with Pakistan, you need one type of strategy. If you want to fight with China, they have got more number of armed forces. How do we go about? We cannot just get the emotional and go to the war. We have to think of ways, we have to think of the strategies. So if you want to fight on two fronts, how do we do it? So all these things have to be thought of. So you see here, a simple concept of first order differential equation gives us some idea about the importance of the strategy and the estimate of people we are likely to lose in the war, even if we ultimately win the war. For example, as I told you, in 1971, the war started on 3rd December 1971 and the war ended on 17th December 1971. It was a 14-day war under the leadership of Indira Gandhi, the then Prime Minister of India. It was a very comprehensive win. But even then, we lost a lot of soldiers. So, but we liberated Bangladesh, right? So we'll have to see what is that we are going to gain and what is that we are going to lose. If we think what we are going to get is more important, then we should not mind to sacrifice certain things. So the strategy becomes very, very important. Then I don't know what is the time now. The time is 11:41. How much time do I have? Hello? Hello?
Sir?
How much more time do I have?
You can have 15 more minutes, sir. You can extend it also, not an issue.
I can extend for about half an hour?
Yeah, you can, sir.
Okay, so then I'll skip this particular model, Markov chains. Markov chains is very important in, computer, this thing. But anyway, I'll skip it because diffusion process is a very simple example. You see, there are two adjoining cells separated by a permeable membrane. This is called diffusion process. And suppose the fluid flows from the first cell to the second one at a rate that is numerically equal to 3 times the value of the first cell. Then it flows out of the second cell at a rate that is numerically equal to twice the volume in the second cell. Let X1T and X2 denote the volumes of the fluid in the first and second cells. Assume that so you see here, there is cell 1, cell 2. fluid is flowing from cell 1 to cell 2 at a rate 3x1t. Amount of fluid present in cell 1 is called x1. Amount of fluid present in cell 2 is called x2. So it is flowing at a rate proportional to 3 times the amount of fluid present in cell 1. So it is going at a rate 3x1t. Then cell 2, it is going out at the rate of 2x2t, right? So now we have to calculate what are x1 and x2. The change in volume of the fluid in each cell is the difference between the amount flowing in, amount flowing out. Since no fluid flows into the first cell, we have dx1 by dt is equal to minus 3x1t. You see here, no fluid is coming inside. So it is only going out. So dx1 by dt is equal to minus 3x1t. Then second cell, you have inflow 3x1t. Here minus sign, here it is plus sign. Because it is loss, here it is gain. And from this, 2x2t is going out. So dx1 by dt is equal to minus 3x. So you see, minus 3x1t. dx2 by dt is equal to 3x1t minus 2x2t. So here also, it is a coupled first order differential equation. But there are two. x1 is an unknown, x2 is unknown. So what is that we do here? dx1 by t is equal to minus 3x1t. dx by dt is equal to 3x1t minus 2x2t. So we solve it using, I think we are all familiar, eigenvalue. I think even the BTech students study eigenvalue problem. So you say, we write it in the matrix form. x1 prime, x2 prime. You see here, minus 3, 0. And 3, minus 2. Minus 3, 0, 3, minus 2, x1, x2. So this is a x prime is equal to ax. Usual eigenvalue problem. But it is a vector eigenvalue problem. So we study the eigenvalues of this matrix, minus 3, 0, 3, minus 2, minus 3 and minus 2. I'm sure all of you, or even the students, are familiar with the eigenvalues, and we get the eigenvectors. Then you have the solution, xt is equal to x1t, x2t, constant of proportionality into the eigenvector, constant of proportionality into the eigenvector. And we have initial conditions, b1 equal to 0, b2 is equal to 125. We are given the initial conditions. Therefore, the volume of fluid in each cell at time t is given by so and so, so and so. You see here, a simple problem. We have used the concept of first order differential equation, ordinary differential equation, coupled differential equation. Then we have, the so-called concept of what you call eigenvalue problem, right? Eigenvalues, eigenvectors, initial value problem. So many concepts we used to solve this simple problem, and we got the solution. This shows the potentiality or applicability. Normally students think, what is the use of eigenvalue? When we calculate, x prime is equal to, we simply calculate eigenvalues, eigenvectors and so on. Does it have any application? Is it simply a useless concept? No. Every concept we study is useful. So this is one example. Then mathematical modeling of epidemiology. Today, this has become very important because we are facing this COVID-19 problem, corona, right? This biomathematics, epidemiology, population dynamics, these are all very important. They are being studied for the last 3 decades, in fact. The rate at which population grows, the rate at which epidemic grows, right? These things are studied through mathematical modeling also. In fact, after the corona has started, the Singapore, Mumbai School of Economics, Niti Aayog, everybody tries to study using the mathematical modeling also. Of course, you see, the corona is very peculiar because it is mutating. It is, changing its shape. So many things are happening. Nobody is able to predict actually. Now there's a second wave. US third wave has started and so on. So ultimately, we may not get an accurate, what you call outcome. But certainly, this shows the applicability and the potentiality of mathematical modeling in the concept of epidemiology. So I think I'll simply skip. Scientists can wage an effective war on disease only if we as a nation and scientific community harness the energies of many disciplines, not just biology and medicine. Allies must include mathematicians, physicists, engineers, and computer and behavior scientists. So this was given by Harold Varmus, Nobel laureate medicine 1989, and former director National Institute of Health, USA. Okay, so I think I'll skip these things. What is epidemiology? It is a discipline which deals with the study of infectious disease in the population. It is concerned with all aspects of epidemic, spread, control, vaccination strategy, and all. What is a disease? Condition of the body or some of its part in which the functions are disturbed, causing a departure from normal state of health. Non-infectious diseases, infectious disease. Acute, stay for a short period. Influenza, chickenpox. Chronic, stay for a longer period. Hepatitis. Mathematics and mathematical representation and analysis of infectious disease has been central to infectious disease epidemiology since the discipline is a discipline. It is the fundamental importance to our growing understanding of pathogen evolution ecology. Mathematical models have successfully explained previously puzzling observations. Fundamental to growing importance of mathematical epidemiology has been the integration of mathematical models with rigorous statistical methods to estimate key parameters of these models. In the absence of reliable data, mathematics can be used to help formulate hypotheses. As I told you, estimation of key parameters, that constant of proportionality, that lambda E, lambda F, which I mentioned, we need to know the values of those parameters. For example, radioactive decay, because it is something which you can see, you can estimate. Corona, you can't see. So to estimate the parameters, we use statistical methods, right? Epidemic modeling helps to understand, if possible, control the spread of the disease. In this context, following questions. So this is very important. Now, what is the need of the hour? We need to control corona. How it can be controlled? What are the conditions we should create? How fast the disease spreads? How much of the total population infected or will be infected? Control measures, effects of migration, environment, ecology, etc. Persistence of the disease. Now we'll take a simple model, deterministic model with a removal. Simple deterministic model. If in a given population time t, let capital S be the number of susceptibles, number of those who can be infected. For example, Andhra Pradesh population, that is ST. IT be the number of infected persons in the population. RT be the number of those removed from the population by recovery, immunization, death, hospitalization, by any other means. Okay, some people have recovered, so they are not in the population. Some people are immunized, some people died, some people are hospitalized, so they cannot infect anybody else. So if NT is a total population, ST, that is the number of susceptibles, IT, infected, RT, removed, that is equal to a constant. We first consider simple epidemic models, models in which there are no removals. Let N be the initial number of susceptible of the population in which one infected person has been in, so that ST plus IT is equal to N plus 1, S0 is equal to so and so, I0 is equal to 1. Okay. Due to infection, number of susceptible decreases, number of infected persons increases. So you see, usual principle. The rate at which susceptibles change, it only decreases. For example, Andhra Pradesh population, 5 crores are there. It can only decrease now. If people get infected, it cannot increase. So it is negative. Infected persons can only increase, it cannot decrease. So it is positive. And we say it is proportional to, like there in the army, we said product of the enemy force and army force, here susceptibles and infected persons. So minus beta SI plus beta SI from 2 and 3. So you see here 2. ST plus IT is equal to N plus 1. So ds by dt is equal to minus beta S into I means I am substituting N plus 1 minus S. So you integrate and using 2, we can solve for this one. So limit tending to the t tending to 0, this is 0, IT N plus 1. That means ultimately all the people will be infected and susceptible becomes 0. So that of course common sense also says. Our common sense says, suppose there are 5 crore people are there. Ultimately what can happen? Everybody will get infected. So infected persons N plus 1, this is 0. So our model, whatever we have done, it coincides with our understanding based on common sense. So this model seems to be all right. Okay. So then these are simple things. I will skip these things. This also I will skip. I will skip. Yeah. A formulation. This is another model. General delivery model with a removal. Let the infected persons be removed from the system at rate gamma. So our system of equations becomes earlier, ds by dt is equal to minus beta Si. Di by dt, here there are removals. Earlier we said there are no removals. So beta Si minus gamma I. So beta I into S minus so and so. We are giving a particular parameter here, rho, dr by dt, rate of removal, it depends upon gamma I. Initial conditions S0 is equal to S0 0, I is equal to I0. Initially, removal is 0, S0 plus S0 is equal to, so we get the simple equations. So and so, I think I'll skip these things because not much time is left. We already 11:53. So ultimately, so we take asymptotic cases. You see, ultimately, S0 is there less than rho, dIdt initial negative, so and so. That means I'll give the final conclusion. A stage may be reached when all the infected persons are immediately removed. Thus, an epidemic builds up only when the density of susceptibility is high, owing to overcrowding, and the rate of removal is low due to inadequate isolation. On the other hand, if the isolation conditions are good and the density of susceptibility is low, the epidemic fades out. You see here, isolation conditions are good. That means you should have facilities either for treatment or for isolation. You see, as soon as this epidemic broke out, we tried to create isolation facility. Then we tried to create hospital facilities. And density of susceptibility is low. People should not crowd. That's why this lockdown was imposed. What is this lockdown? Other people come and gather. When the density of susceptibility is high, then the chances of the epidemic getting increased is more. So a stage may be within all the infected persons are immediately removed. Thus, epidemic builds up only when the density of susceptibility is high due to overcrowding. You see, epidemic builds up only when the density of susceptibility is high, owing to overcrowding, and the rate of removal is low due to inadequate isolation facilities. On the other hand, if the isolation conditions are good, density of susceptibility is low, the epidemic fades out. So people say, what is the purpose of lockdown? Now again, we are getting cases. It is not true. Because of lockdown, cases were less. That gave time for the government to create medical facilities. Earlier, you imagine, March 15th, March 16th, when the lockdown was imposed, masks were not available. Sanitizers were not available. The so-called ventilators were not available. Oxygens were not available. Beds were not available. Nothing was available. If there had been no lockdown, there would have been an explosion of cases. People would have been crying like it happened in Italy and so on. But because of those experiences, lockdown was imposed. So that reduced, you see here, density of susceptibility is low, and therefore isolation conditions are good. So this gave us an opportunity to create isolation conditions, hospitalization conditions. That's why, you see, despite 130 crore population, many people are illiterate, sanitation conditions are bad. Still, I don't say number of people did not die, but still, even World Health Organization said India has done a wonderful job. You see, the advanced countries, USA, their population is only 30 crores. They have got so many facilities. They say superpower. Italy, their population is nothing compared to the European countries. Compared to them, we could control because, these conditions. So this model goes to show. So whatever the outcomes of this model, it is not that we don't know. We know these outcomes. If people do not gather, the epidemic does not spread. But this model also tells the same thing. That means this model is a reasonably valid model. So this we can apply to estimate. Now we can do quantification. Suppose initially we saw so much of population, say Andhra Pradesh, 5 crores population is there. If so many removals are there, then how many people will be there after some time? So we estimate, now you see, keep seeing. So many people have already got corona and so on, all sorts of statistics to find out. So quantification is possible, but sometimes they give rise to wrong pictures also because of several reasons. The model may not be good. Initial conditions may not be good. The technique we have used may not be good. Thomas Edison, when he invented electric bulb, it was not the first time he gave it that. He made 99 attempts, failed. 100th time he got it. So those 99, you cannot call them failures. So this particular element you can't use as a filament. This particular element you can't use. So you are ruling them out. So all these failures are stepping stones to success. So in fact, what the model which I have presented is only a very, very preliminary model, simple differential equation, but that shows the applicability, utility, potentiality of mathematics in a very complex situation like understanding COVID-19, spread of COVID-19, how to take measures, under what conditions the epidemic builds up, under what conditions the epidemic fades out. These things could be known using a very, very crude model. If more sophisticated models are used, you can get better results. Okay? Then I don't know how much time. Can I take another 15 minutes? Hello? Hello? Hello?
Yes, sir. Is it audible?
Yeah, can I take another 15 minutes?
Okay, sir. Okay, sir.
Okay. Yeah. Yeah, actually, this is a very important and beautiful, fascinating topic, biofluid dynamics, application of principles of fluid dynamics to biological systems. Since time is not there, I'll quickly run through it. Actually, it is a study of biological systems using the principles of mechanics and in particular fluid dynamics. So here, when we say biofluid dynamics, it is essentially study of human body and its components by the application of principles of mechanics oriented to medical application. The fundamental assumption is world of living, world of non-living are governed by the same laws of physics. That is, we know certain laws. Laws, conservation of mass, conservation of linear momentum, conservation of angular momentum, conservation of energy. Human body does not disobey any of these things. Okay. Anyway, I will quickly run through. What are the aims and objectives? It is revealed that many analogies exist between human body frame and engineering systems, and both of them function more or less similar mechanical principles. A collaborative study would enable the scientists to understand biological systems better. This understanding in turn would help in the designing of artificial limbs and in the diagnosis of diseases. So this is a contribution of mechanics, fluid dynamics, engineering to biological system. So we are able to design artificial organs today because of the application of engineering principles to biological systems. And we are able to improve the diagnostic techniques, ESR, erythroid sedimentation rate, measurement of blood pressure. All these things are improved over the centuries because of the application of principles of mechanics. Second thing is very important. Nature has provided excellent engineering systems to living beings, which are far more superior and novel than their counterparts of mechanical systems. And the better understanding of biological systems may help us in sophisticating the existing engineering system. This is a very important one. I'll give you a simple example because I may not have time to present the entire model. You take, for example, kidney, human kidney. Human kidney is, in human body, there are two kidneys. Kidney is one excretory organ. It excretes the end products of body metabolism, like skin, like lungs, like, for example, the digestive system and so on. So it excretes the system, these things. When in kidney, the functional unit is called nephron. That's why a kidney specialist is called a nephrologist. Each nephron works independent of the other. Now you see, for example, when the kidneys are damaged, somebody is put on a dialysis. Okay, dialysis unit. What is done there? The body, human body, it is connected to a machine. Blood is drawn out of the body. It passes through the machine. It purifies the blood and sends it back to the body. So each nephron in the human body is like one dialyzing unit. One dialyzing unit is a very big unit. And that means there are 20 lakhs of such units in the human body. How costly is dialysis process? How big is that one? How much time does it take? But you see, human body, there are 20 lakhs of such units. And it does automatically, without our knowledge. I am speaking, you are listening, but the impurities are getting filtered. Later we pass out in the form of urine. So you see the level of sophistication of human body. Can we imagine in the engineering domain such a system? You take, for example, the joints. We have the elbow joint, we have hip joint, we have neck joint, we have ankle joints. Joint is like a bearing surface in mechanical engineering. Your bearing surfaces, you have a lubricating fluid. You take any machine, how much warranty they give? 3 years warranty. After that, you will have to pay. But you see, these machines, human body, they work for 60 years at least. If we take proper precautions, that shows the level of sophistication of systems in the human body. So if we can understand the principles lying behind the working of these systems, we can sophisticate the existing engineering systems. That would be the contribution of biology to engineering systems. Okay. Anyway, I'll quickly do this. These people are done. I will not go through this because no time. Some of the important cardiovascular, food mixing, flow in renal system, reproductive, and so and so. Yeah. Okay. So you see here, I think I'll quickly run through. For example, when see, this is one carotid artery, normal blood circulation. You see, when we take too much of fat, let us say, too much of oils and so on, this plaque, a growth will come. When the growth becomes too much, there will be occlusion, there will not be flow. That results in, if it happens in the blood artery, we supplies blood to the heart, we call it heart attack. If it happens in the blood vessel, we supplies blood to the brain, we call it paralytic stroke. Okay, both the situations we model using the same fluid dynamical model. That is the beauty of mathematics. Okay, systole diastole. You follow. You take a rubber cuff, inflate with air. When the air in the cuff is more than the maximum pressure in the artery, the blood flow stops. What the doctor does, he slowly releases the valve. Then the pressure here decreases. He puts a stethoscope here, listens. When the pressure in the cuff is slightly lower than the maximum pressure in the blood gushes out. There will be a third sound that is noted as a systolic pressure. The third character changes, disappears. That is noted as the diastolic pressure. We studied this in high school, you know, the so-called principles of, we call it hydrology, hydrodynamics, physics we study. So this measurement of blood pressure simply depends upon the concept of fluid dynamics. Why? Okay, I think we'll quickly, yeah, pulse. As I told you, I think time is not there. The pulse depends upon simply concept of simple harmonic motion only, right? So such an important pulse. Then you see this is an important concept. Why blood pressure is measured in the upper portion of the arm? This is a very important thing. You see here, 1 minute. Yeah. Suppose you take a tub. We all study in school. Suppose you take a tub. You put some water there. What is the pressure there? It is equal to the atmospheric pressure. We call it PA. If you go down, you get the rho GH, which is the force of buoyancy. So the pressure there is atmospheric pressure plus force of buoyancy if you go down. Suppose you give a thrust to that one, then the excess pressure is there. This is the total pressure. Human body, what happens? You have blood, you have this rho GH component, and you have heart is pumping continuously. So the excess pressure generated by the periodic pumping at the heart, that is PE. But the doctor is interested only in PE, not PA, not rho GH. How they are eliminated? When you take this blood pressure through this sphygmomanometer, what you calculate is PI minus PA. So this component is lost. What is this H? H is below the surface. So this brachial artery, where the blood pressure is measured, is at the level of heart. So that is where H is 0. Therefore, this component becomes 0. That is the reason why the blood pressure is measured in the brachial artery, which is the level of the heart, so that you get only PE. It is the pressure generated by the periodic pumping of the heart. So you see, all these concepts depend upon the concepts of fluid dynamics. Okay, so I think I will. So this is one simple model given by Sir James Lytle. He was a Lucasius professor holding Newton's chair, right? Eminent professor. This is a simple mathematical fluid dynamical model. This is the equation of momentum. This is the conservation of energy, or what we call equation of continuity. Then using this simple equation, ultimately he got the wave speed, and he compared it with the experimental value. It differs only by 15%. So Lytle showed by considering a one-dimensional Navier-Stokes equation, you could get wave speed which is within the to an error of 15% compared to the measured value. All these things go to show the potentiality of subject of fluid dynamics in understanding of working of the biological systems. Okay, as I told you, kidney. So this is the kidney flow. In fact, I think time is not there, so I think I should stop. So, so these are some of the processes. Here, as I told you, human body follows all usual principles: osmosis, diffusion. Nothing, it does not disobey nature at all. Human body. That is the beauty of human body, right? Then these are models which were considered in earlier by Massey. Then myself and Professor Piyush Chandra, we did a problem on this one. Way back, it was published in Bulletin of Mathematical Biology. So I'll quickly run through this model. This is the wall. Actually, we got this equation by this curve fitting, by looking at the data given in Guiten's book on physiology and using simple what you call curve fitting. We got this equation, the equation of the wall, then usual Navier equations, the initial conditions, boundary conditions, then method of solution. Finally, we used we called what is that called? 1 minute. Yeah, the pressure drop, mean pressure drop. Mean pressure drop. We have taken the data of rat's kidney, these rat's kidney flow, then radius, and the viscosity, and then we calculated, and we found that its values are quite closer to the experimental values. In fact, when we published this paper, there were so many questions from medical doctors, like urologists, nephrologists, physicians, radiologists, cardiologists, surgeons. They all contacted us, said, we are amazed that the concept of fluid dynamics help us in understanding the working of the kidney. Please share how you have done it. Then we sent all our literature. Okay, why I'm telling you is not to boast about ourselves. It is to show how fluid dynamics, or in general mathematics, helps us in understand physical situations. I've given so many physical examples earlier, and this is a biological example related to kidney. Today you find so many people suffer with a kidney problem, undergo dialysis, spending a lot of money, and ultimately they get into a lot of trouble. So to analyze these cases, how mathematics, how fluid dynamics helps us. Okay, I think I've taken a lot of time, right? So I think I stop my lecture. In the short lecture, I don't know, as I told you in the beginning, I've been giving several webinars in the last 2-3 months. A larger portion of this would have been a repetition for some of the audience. If you are bored, kindly excuse me. Even if one person is benefited, and if he realizes the importance of mathematics and fluid dynamics in analyzing the physical situations like corona and so on, I think I would feel very happy. Thank you so much for giving me this opportunity. It's wonderful interacting with all of you.
Thank you, sir. Thank you for your energetic and wonderful session, sir. So now I request the participant, if you have any questions, please rise. Sir will
Unmute your audio.
address the participants, and sir will answer the questions. Any questions, please unmute your mic and raise the questions.
The voice was on.
Thank you very much.
Okay, sir. Thank you very much for your enlightened talk, sir. Now I request P. Swarajya Lakshmi to give vote of thanks.
Good afternoon, sir. Good afternoon to everybody. Thank you, sir, for your enlightened, energetic, and motivated talk. I hope that most of the participants have gained a lot of knowledge from the input given by sir regarding application of biofluids and importance of mathematics in all the fields. Especially, he pointed out the importance of statistics and linear algebra in nowadays as we are moving to digitalization, and regarding mathematical modeling, how to use mathematics to convert real model to real world, and corona by validation, and a problem coupled model of fighting armies regarding epidemic modeling in corona pandemic situations. We can design artificial organs by biological system. And he has given a crystal clear example and application of mathematics in real life situation, even in your busy schedule. So we have accepted our request to deliver your message at this webinar. And thank you, sir. Thank you so much.
Can I leave now?
Sir, sir, thank you, sir. You can leave, sir. And I request all the participants to fill the feedback form which was posted in both Google Meet and YouTube link for today's session. So we are ending the session. Good afternoon and thank you to one and all. Thank you, sir.
Bye.
Bye, sir.